Welcome to lecture number 2, where we'll be looking at methods of differentiation. My name is Charles. The presentation outline will look as follows. I'll give a brief introduction to the methods of differentiation, look at the product rule in detail, quotient rule, chain rule, then we'll look at successive differentiation method, and then I'll give a reference just to guide the topics are above. There are various methods of differentiation, and this includes the product rule, quotient rule, chain rule, also called function of a function rule, and the like. Each of these methods is discussed here, but like we discussed in the first lecture, we must always remember the standard methods of differentiation. And I would invite that you review lecture number 1 of this series in order for you to familiarize with the standard methods of differentiation. The table here shows the standard derivatives, which were discussed in lecture number 1. We did understand that the derivative of ax to the power n is always ax to n minus 1. The derivative of sine ax is always a cos ax. That of cos ax is minus a sine ax. And the derivative of an exponential function e to the power ax is always a e to the power ax. And that of ln ex is always 1 over x. So with this understanding and with all the examples that we dealt under lecture 1, let's now delve into the details by looking at methods of differentiating a bit more complicated functions that may either be a multiplication of 2 terms or division of 2 terms, or simply that may not terms or functions that may not fall into the standard format. The first method is known as the product rule, and this rule applies where you have a function that has 2 terms that are multiplied together, and these terms are here denoted as u and v. The moment the 2 are being multiplied, they can be differentiated, or you can use product rule of differentiation by simply applying this rule dy over dx equals u, which is the first function, differentiate the second, plus take the second function the way it is, multiply by derivative of the first. Again, this is known as the product rule. Let's do an example. Find the differential coefficient of y equals 3x squared sine 2x. If you look at this example, you'll notice that 3x squared is the first term, while sine 2x is also the second term. And the two terms, 3x squared and sine 2x, are being multiplied. We can denote the first one as u, while the second one as v in this function. And once we do that, we can now apply the product rule, which is given here, dy over dx being, take the first function the way it is, differentiate the second, plus take the second function the way it is, multiply by the derivative of the first. And so for this example of y equals 3x squared sine 2x, our u is 3x squared. When we differentiate the second function, which is our v in this case, sine 2x, we get 2 cos 2x, plus get the second function the way it is, which is our v sine 2x, differentiate the first, which is 3x squared, and it will give us 6x. Simplify this, we get 6x squared cos 2x plus 6x sine 2x. Then we can further simplify the 6x and factor it out. You are going to have 6x open bracket x cos 2x plus sine 2x as your final answer. We can do the same by looking at the second example. In the second example, let's have a function y, 3 root x ln x. In this example, 3 root x denotes the first function u, while ln 2x here represents the second function v, and the 2 are basically being multiplied. And therefore, we can find the rate of change of y with respect to x in such a way that this y, which is equal to 3 root x ln 2x, can be rewritten by removing the root in the root symbol in the x, since by making it the power of half, since we know that the square root of 4 is the same as 4 to the power half. Therefore, the square root of x here is the same as x to the power half. So again, this becomes our u, this becomes our v, and then we can now apply the product rule, dy over dx, which is u dvx plus v du dx. Take your u the way it is, it will be 3x to the power half. Differentiate ln 2x, you get 1 over x, plus ln 2x, which is our v the way it is. Differentiate the first function, which will be the first function being 3x to the power half, and we'll get 3 over 2x minus half, and this minus here being a simplification from half minus 1, giving us minus half, and then this is being multiplied by 3 over 2. We can further simplify this by simplifying this part here. If we simplify this, this will come to that, which will later on reduce to 3x minus 1 over 2, factoring out the 3x minus 3x to the power minus 1 over 2. This gives 1 plus 1 over 2 ln 2x, and again this can be simplified to simply 3 over root x, 1 plus 1 over 2 ln 2x as our final answer. We can move further now to look at the second method of differentiation, which is the quotient rule. Quotient rule is applied when a function y has two other functions, and they are such that these two functions are dividing each other. You have u over v. Therefore, you can apply the quotient rule, which is dy over dx equals v multiplied by the derivative of the first function, where the first function in this case is basically this one, then this becomes the second function. So v multiplied by derivative of the first function minus, take the first function the way it is, multiplied by the derivative of the second function, which is v, dv over dx, everything else divided by v squared. And this is what is known as basically the quotient rule. So let's do some examples to illustrate the application of this quotient rule. Let's have this example, y equals 4 sine 5x divided by 5x to the power 4. Using the quotient rule, 4 sine 5x becomes the first function u, okay, and the 5x to the power 4 becomes the second function v, and we have to take note that v is always the denominator while u is the numerator, and applying the quotient rule, which is given here, you notice that we can find du over dx as du over dx, the derivative of this first function here, which is basically 4 times 5 cos 5x, being simplified to 20 cos 5x. The derivative of the second function, which is dv over dx, will be 5 times 4, which gives us 20x to the power 3. So the derivative of the second function, dv over dx, giving us 20x to the power 3. And then inserting these two into the quotient rule formula, you'll have 5x to the power 3, which is your v, multiplied by du over dx, which is 20 cos 5x, minus the u, which is 4 sine 5x, multiplied by the derivative of the second function, which is 20x to the power 3, divided by v squared, which is 5x to the power 4, with a square here coming from the formula. And then simplifying this and factoring out the common denominator, you can have 5 times 20 there, giving us 100x to the power 4 cos 5x, minus 20 times 4, giving 80x to the power 3 sine 5x, divided by 25. 5 squared is 25, x to the power 8, x to the power 4 multiplied by 2 is basically x to the power 8. Simplifying this further and dividing, you get the final answer, which is 4 over 5 x to the power 5, in bracket 5x cos 5x minus 4 sine 5x as your final answer. So that's on the quotient rule. Let's move further by looking at the next, which is known as the chain rule. The chain rule states that you can find the derivative of dy over dx by equating, by first of all finding the derivative of y with respect to u and multiplying it with the derivative of u with respect to x. This is called the function of a function rule, or simply the chain rule. Let's do an example to illustrate. If you are given y equals 3x minus 1 to the power 9, you can let everything in the bracket be equal to u, therefore y equals 3x minus 1, and then find the derivative of this, which is du over dx, and in this case, we get a 3. We get a 3 here, and then you can also find the derivative of y with respect to u, the derivative of this function, which is dy over du, and this will become 9 u to the power 8. So since you have now two derivatives, dy over du and du over dx, you can find dy over dx as dy over du times du over dx, which is simply dy over du is basically 9u to the power 8, and while being multiplied by du over dx, which is 3, and this reduces to 27u to the power 8. And then from here now, you can substitute the value for y, since your u is basically 3x minus 1. You're substituting it here, you have 27, 3x minus 1 to the power 8 as the final derivative of the function y, 3x minus 1 to the power 9. The second example here, you are given y equals 3x, 3 cos 5x squared plus 2. Again, you can apply the chain rule by simply taking what is in the brackets here, you let it be equal to u, and then find the derivative of that, which is du over dx, giving us 2 times 5, which is 10x, and then again find the derivative of y with respect to y in this equation, since you've let this whole thing here being equal to u, therefore dy over du is equal to minus 3 sine u, and then multiplying and applying in the formula, you have dy over dx being equal to dy over du, which is that part, and then multiplied by du over dx, which is that part, and then multiplying these gives that kind of a product, and the final one being equal to minus 30x sine u. And then you can substitute the value for u, since you said your u is 5x squared plus 2, and then this is what you have here, and your final answer will become minus 30x sine 5x squared plus 2. Can move on to the next, which is basically successive differentiation. Successive differentiation simply means that you differentiate a function once, and again, once you differentiate the function the first time, you get dy over dx, which can be written as this. You can also write this as simply y with a dash at the top. But if we differentiate the derivative of of y a second time, then you have what is known as d2y by dx squared, d2y divided by dx squared. This can also be written as simply y with 2 dash, or you can write it as a function in form of f with 2 dash with x here. And take note, if it is the first derivative, it is f with 1 dash, whereas if it is the second derivative, we're differentiating the same function the second time, it is with 2 dashes here, which can also be written as y with a double dash. Again, this function can be differentiated a third time to get d3y over dx to the power 3. And then you can also again differentiate this a fifth, a fourth, and even a fourth time, and so on. This gives birth to what we'll later on discuss when we talk of first order differential equation and second order differential equation. Take note, when we equate this to 0, we make a first order differential equation. And when we equate the second derivative to 0, we have basically formed what is known as the second order differential equation. But we'll come to that. For now, I just want you to know that when you differentiate a function once, it is a first derivative and it's of order 1. When you differentiate a function a second time, it's a second derivative and it's of order 2. And again, when you differentiate a function a third time, it's a third derivative and it's of order 3, and so on and so forth. So with that, let's give an example to illustrate. Suppose you have y equals 3x to the power 4. When we differentiate this, the first derivative of this, dy over dx, it will be 4 multiplied by 3, which is 12x, 4 minus 1, which is x to the power 3. That's the first derivative. If we differentiate this first derivative a second time, we're going to have 3 multiplied by 12, which gives you 36, and then 3 minus 1 there, giving you x to the power 2. So this becomes the second derivative of the function y equals 3x to the power 4. You can also choose to differentiate this second order, the second derivative a third time, which will be 2 times 36, which is 72. X to the power 2 minus 1 just gives you x. Therefore, the final answer becomes 72x. That becomes the third derivative. The fourth derivative will simply be 1 multiplied by 72, which is 72. Then x to the power 1 minus 1, which is x to the power 0, which will give you a 1, and 1 times 72, giving you just the fourth derivative as being 72. The fifth derivative in this case is differentiating of a constant, and whenever you differentiate a constant, you're going to get a 0. This marks the end of our presentation, and again, I've given this important reference